Okay guys, so I promised you I would do these examples for you on a video so that you have access to watch them before the test on Friday. All right, so it says a rocket moves upward starting from rest. So this is the one we did in class, but we sort of rushed through it. So I want to make sure you guys have this example. This is a really big problem for the test. Starts from rest with an acceleration of 29.4. Remember, that's because it has like some sort of thruster or something pushing it upward. It does this for 3.98 seconds. It runs out of fuel at the end of the 3.98 seconds, but does not stop. So remember, it just keeps floating up and cruising up until it runs out, until acceleration of gravity brings it back down. All right, so that's part one. And then part two, it doesn't actually stop. So here's the picture, right? So it's a rocket, goes up, accelerates till here, then cruises up until it eventually stops and then comes back down. We're only worried about the max height, so we don't need to worry about the part coming back down. So this part, the A is just gravity. And for this first part, the A is the 29.4 from the thrusters, okay? In part two, whatever the final velocity is for part one will become the initial velocity for part two. We know A is negative 9.8. And we know when it hits the max height, it's going to stop just for a split second. So we can give the final velocity for part two can be 0. Okay. And we want to know the maximum height, meaning we're looking for the displacement of the whole thing. So we'll do like displacement of part one plus displacement of part two. Okay. So displacement for part one, we don't have V final, so we can use this equation. And we plug in. Okay, and we should get about 233 meters, if I remember correctly. Okay. And then for part two, in order to find the displacement, we still need initial velocity, but remember we find it because it's going to be the same as the final from part one. So I'm going to solve for the final velocity in part one using this equation, just the easiest. 0 plus. Okay. And if I'm remembering right, it's about 117 meters per second. So that's how fast it was going when the thrusters died, okay, or the fuel ran out. And so then that's the initial velocity starting here, and then it will slowly decrease in velocity because gravity pulls it down. So there. So displacement here, we want to use, we don't have time, so we want to use this equation. Okay. So V final squared is 0. Looking for displacement. So I'm going to do 117 squared, and then I'm going to move it to the other side, so it's negative 13,689. 2 times negative 9.8 is 19.6. And we get 698. So this is 698 meters. So then if we just add those, the total height or the max height would be 698 plus 233, which would be 931. Okay, and that's the end of that problem. Okay. All right. And then we didn't get to number 3 or 4, so I'm just going to do both for you here. So a fish is dropped by a pelican that's rising steadily. So we have an initial velocity of 0.5. That's how fast the fish and the pelican are dropped, or are together, right? They're moving upward with that speed. After 2.5 seconds, what is the velocity of the fish? So the first fish gets dropped, but because it was initially with the pelican, it was initially moving up with this speed. So then we want to know the final velocity after 2.5 seconds. We know that it's going to accelerate down toward the Earth due to gravity, so we know the acceleration. So if we're looking for final velocity, I think we only have one option right now, it'd be this equation. Okay, so 0.5. So I get VF equals negative 24 meters per second. Remember, it's negative because it's falling down, so that's okay. That was kind of like part A. And then part B says how far below the pelican is the fish after 2.5 seconds. So let's see. So we want to find displacement of the fish. So I don't know how to draw a pelican, but there's a bird, and then there's the fish, right? And it dropped it. So the bird's actually moving upward. The fish is now moving downward. So the displacement of the fish after 2.5 seconds, we can use this one. A t squared. And plug in, we get 0.5 times 2.5. Careful with your order of operations here in your math. I do this part first. Then I solve this separately. Because it can get a little weird here. So you get displacement equals negative 29.4 meters below where it was dropped. But keep in mind, this is tricky. It's, yes, 29.4 meters below where it was dropped, but in that 2.5 seconds, the pelican has continued to move upward with this speed of 0.5 meters per second. So the pelican has moved, it has a speed of 0.5 meters per second because it's flying, right? It's not dropping. And the time has been 2.5 seconds. So its displacement upward has been, let me use this equation. Has been 1.25 meters. So the fish is 29.4 below where it was dropped, but the pelican is 1.25 above where it was dropped. So how far below the pelican is the fish? So it's this plus this, but remember this is negative. So I want to make sure the negative is just the direction. So it's 29.4 plus 1.25. So it's actually 30.7 meters below. That's a 30, not an 8. 30.7 meters below the pelican because the pelican was rising as the fish was falling. Okay, so hopefully that makes sense. All right, and lastly, two students are on a balcony 19.6 meters above the street. Okay. One student throws a ball vertically upward at, so let's just say 1. So initial velocity is 14.7 meters per second. At the same time, the other throws a ball vertically downward, same speed. So ball 2, its initial is negative 14.7. What's the difference in time each ball spends in the air? What is the velocity of each ball as it hits the ground? All right, so let's see. So A is negative 9.8. Let's see. Okay, so we know ball 2 is also negative 9.8. And we know ball 2's displacement is going to be negative 19.6. Okay. But ball 1 is actually going to go up, hit a max height, and then fall back down. So we actually have to figure out how high up it goes first, because we have to account for that. So if it goes all the way to a max height, we know at the very top, it's going to be at 0 meters per second. So I'm going to say at top. Okay. So let's see how far it goes up. Actually, do we need that? Yeah. So how far it goes up. So displacement we could look for. So it'd be VF squared equals VI squared plus 2AD. So 0 equals 14.7 squared to negative 9.8 D. Solve for D. So you get 11.0 meters. Okay. All right, and then we got to figure out how long that took. So we'll go t. Okay. And we could use the first equation, the VF. I'm still in part 1 here. So let me actually. Part 2 is going to be easier. VF, VI plus AT. So VF is 0, VI is 14.7, A is negative 9.8, looking for T. So we get T equals 1.5. So it takes 1.5 seconds on the way up, and then it's going to take another 1.5 seconds to come back down to that height of the cliff. So that's 3 seconds for the ball to get back here. And what's really cool is that motion is symmetrical. So by the time it gets back here, its velocity will be negative 14.7 as it heads down. So really, we don't have to do anything with part 2 because the extra time, so it says what is the difference in the time each ball spends in the air? Well, ball 1 is going to spend 3 seconds longer than ball 2, okay, just to get up and then back down to where ball 2 started. And the velocity of each ball as it hits the ground, so then we're just looking for final velocity. So we could find, let's see how long it takes this. Actually, sorry, let's just do final velocity here. So, and they actually should be the same. So let's see, final velocity would be this equation. So v final squared equals negative 14.7. Make sure that the squared includes the negative. So I get square root, so I get v final equals 24. It should be negative. Make sure that's clear. Negative 24.5. Sorry. And they should be the same because they're going to actually eventually, this one when it comes back down, will match exactly the same thing as this one. It will be going down at 14 meters per second, 14.7 meters per second, and it has the same distance and all that. So the final velocity should be the same for both, but ball 1 will take 3 seconds longer because it had to head up before it came back down. Okay? This is, you're not going to see anything like this on the test. This is a tougher one, but you should start to kind of get used to this type of problem because that's what you're going to start to be seeing. Okay? All right, you're all set.